Good evening, everyone. Welcome to the 2025 NAG Memorial Endowment Lecture. So, most of you have heard of Professor Subhashish Nag, who was a mathematician at IMSC, and he worked in complex analytic geometry, particularly Teichmüller theory. And he wrote the book, The Complex Analytic Theory of Teichmüller Space in 1988 at the age of just 33. It's a very comprehensive book on the subject, and it's still like an important book in the area. It was one of the first books of this kind, like overall on Teichmüller theory, the complex analytic theory of Teichmüller space. And unfortunately, he passed away at the young age of 43. He was awarded the Bhatnagar Prize that very year, but before this is the highest sort of academic prize in India in science, awarded to scientists below the age of 45, but he passed away before he could even collect the prize from the Prime Minister of India. So this series of lectures is part of an endowment from his wife, Mrs. Sutapa Nag, and it's been going on since 2002. The first speaker was Dennis Sullivan. And this time, we are really lucky to have Professor Nikita Nekrasov, who brings together in the spirit of Subhashish Nag mathematics and physics. I always thought he was a mathematician, but they tell me he's a physicist. So, you know. And I just request Nemani to introduce the speaker in a little more detail.
Thanks, Amritanshu. Yeah, so we are very fortunate to have Professor Nikita Nekrasov here to deliver this Nag Memorial public lecture. Professor Nekrasov is an eminent theoretical physicist who has made profound contributions to the interplay between physics and maths, as Amritanshu has already mentioned. We will hear about some of these from him later on in this week, including this talk. He is the founding faculty member of the Simon Center for Geometry and Physics and a professor at the Young Institute for Theoretical Physics at Stony Brook University. He was formerly a faculty member at IHES and he joined Stony Brook in 2013, where he has been ever since. He obtained his PhD from Princeton in 1996 at a very young age under the guidance of Professor David Gross. Professor Nekrasov's research focuses on quantum fields and strings, as I mentioned, particularly on some fascinating connections between two-dimensional conformal field theories and supersymmetric quantum field theories in higher dimensions, 4 and above. One of the aspects he is famous for is the application of methods of equivariant localization to compute partition functions of particular four-dimensional supersymmetric quantum field theories, including subequation theory. He is also credited with elucidating the so-called BPS-CFT correspondence, about which we will get to hear in the next two technical talks part of these NAG lectures, which is a set of results between SUSY quantum field theory, supersymmetric quantum field theories in D equals 4, 5, and 6 dimensions, and two-dimensional integrable and conformal field theories. Professor Nekrasov received numerous honors, including Hermann Weyl Prize in 2004, the Compositio Prize in 2009. I'm sorry, I don't know if I've pronounced it right. Danny Heinemann Prize for Mathematical Physics in 2023. In today's NAG lecture, Professor Nekrasov is going to talk about emergent space, from counting boxes to space-time form and beyond. Without further ado, let me welcome Professor Nekrasov to deliver his lecture.
So, thank you very much. It's an honor to participate in this now 20 years old long tradition of NAG Memorial Lectures. It's especially an honor to continue the tradition started by my colleague Dennis Sullivan, my double colleague in a sense, because he was at IHS a long time ago, and then in Stony Brook, and so I kind of tag along. The topic of my lecture is something which might be dear to heart to many people in India. At least this is the perception of Western people who think about Indian culture. What is that Indians think about? Of course, it might have nothing to do with actually what Indians think about. But when we Westerners, and Easterners, whatever, so I'm from the Northerners, think about the main contribution of India to the world civilization, it's this concept of multiverse in which we simultaneously live, where there is this illusion of the material world which we are fed by, but there is also something else which might be behind the veil. And so remarkably in modern theoretical physics, well, maybe not so modern already, this idea of emergence, of emergent phenomena, I guess first arose in the context of condensed matter physics and sort of propagated into other parts of physics. So today I'm going to talk about emergent space, or maybe Maya, as you might call it. So something which, a physical system which has its intrinsic definition in terms of some degrees of freedom, which suddenly in some regime of parameters behaves as space-time or geometry of some kind. So another title of my talk is Playing with the Building Blocks of the Universe, because we will be counting structures built out of very simple elementary blocks, like child playing with toys like cubes and building various constructions. And the result of this play, of this entertainment, will be emergent structures resembling space-time geometry. So, as I said, the world around us is full of emergent structures, which we can see in many, many different phenomena, from the shapes of lightnings and snowflakes. And if you have certain tools, you can observe them in the behavior of quantum many-body systems, in, for example, strongly correlated electrons exhibiting fractional Hall effect, and relativistic invariance of electrons propagating in layers of graphene. So the emergence, so these different examples have different kinds of emergent structures attached to them. So in this latest example, the graphene, which is a non-relativistic system, so it's something you can build, as you know, from using the pencil and a little bit of scotch tape. So it has nothing to do with relativistic physics at the first glance, but nevertheless, when the electrons which propagate in these structures, highly organized structures, exhibit features similar to the features of relativistic quantum particles. And so people have speculated that maybe the space-time itself is actually an emergent concept. So that, what do I mean by that? So classically, and by the way, I didn't know before coming here that you have this equation, this same equation written on the on the board. It's just that there are not so many good equations. So classically, space-time is from mathematicians. It's a pseudo-Riemannian manifold described by Einstein equations. And by classically, I mean at large scales. So at the scales from like stars and galaxies and clusters of galaxies, and maybe black holes, to the scales we can observe without special tools. But we actually don't know whether this picture persists to smaller scales, like sub-millimeter already. We don't know whether Einstein equations are a good description of space-time geometry. And so if you go even at smaller scales, let's say distances of the order of Planck scale, 10 to the minus 33 centimeters, we don't know. Maybe space-time will look as something completely different. So this is a quote from Monty Python, if you could recognize it. So it could be built out of something discrete, and these discrete structures may have something to do with the structure of space-time, or it could be something completely fluctuating like space-time foam proposed by Hawking. In fact, proposed by French writer Boris Vian much earlier. He called it the time foam in the title of his book, Écume du jour. But of course, Hawking meant something more sophisticated than Boris Vian. Or it could be that this is, in fact, a system which, as its intrinsic degrees of freedom, has something which doesn't look like space-time at all, like maybe a collection of spins, as people today discuss in the context of the so-called SYK model. So it's something which has an intrinsic definition, maybe has a Hamiltonian, has some dynamics, which is ordinary quantum mechanical dynamics. Nevertheless, when you average things over large scale, there are some observables of those which are built out of the elementary degrees of freedom, being the cubes or spins or something else, which will look like the space-time geometry, like described by Einstein. Now, people played with this idea for some time now. The idea that space-time may be discrete at small scales, and then the continuous and smoothness, the continuity and smoothness in topology, they emerge at large scales when you maybe send some parameter to 0 or to infinity or something. And so one approach which was popular when I was finishing my high school was to approximate space-time geometry by some discrete structure. And by the way, Dennis Sullivan contributed to the mathematics of that. So, for example, something like built out of triangles, so a triangulated structure, or a simplicial complex for mathematicians. So it's something combinatorial. So you just have to tell how the triangles are attached to each other, but intrinsically the triangles are the same. So there is no distinction, and the complexity arises from different ways of attaching triangles by the edges to each other. And then, so you replace the continuous geometry, or smooth geometry, by something discrete with some flexibility, which is also discrete, and then you develop tools for averaging, for summing over all these possible discrete structures. So one way to do this is to draw the so-called dual graph. So I don't know if you can see it. So if I had this structure built out of triangles, now I can try to draw perpendicular lines to the edges, and they will form this structure which is called a fat graph. So it's a graph, but the edges are slightly thickened, and it gives you a way of encoding certain cyclic order of vertices or edges at the vertex. So these graphs were found by Gerhard Hooft, whom you also have as on one of the photographs at the corridor, in the study of, he was trying to develop tools of analyzing theories of strong interactions, assuming that the number of colors of kind of intrinsic degrees of freedom of elementary constituents goes to infinity. And so he was trying to do this directly in four-dimensional gauge theories, and it was very complicated, but then some people said that why don't we try to do it in a simpler context, and that will still give us some interesting results about the summation over these discrete structures. And maybe if we tune some parameters, we'll get something which will look like smooth geometries which are slightly fluctuating, which is what you want to quantize Einstein theory. And so, developing 't Hooft ideas, people realized that if you just do something very finite dimensional, compute an integral over finite dimensional matrices, again, this goes back to the work of yet another person whom you have on the walls here, Eugene Wigner, who was, at some point said that instead of solving for the spectrum of a particular Hamiltonian, which we don't know, let's try to assume that the Hamiltonians describing the, let's say, atomic spectra are random and try to get some statistics. And then it was developed by Dyson. And so that led to the studies of ensembles of matrices. So you try to average over n by n matrices with some measure, and it turns out that if you try to study this quantity in the limit when the size of the matrix goes to infinity, then it has the expansion in some combinatorial objects, which happen to be these fat graphs of 't Hooft, which are the same thing as triangulated Riemann surfaces. And so there were some rules developed, following 't Hooft actually, which build, so depending on what is the potential V of m, if it has a quadratic term, which would correspond to a propagator, and cubic terms, which would correspond to vertices of these graphs, you could have higher order vertices and build more sophisticated measures. So that will, in the limit when this parameter n goes to infinity, this matrix integral will have the form or the shape of the generating function of integrals over the spaces, modular spaces of Riemann surfaces of arbitrary genus, number of handles, which is the subject of, so this modular space is covered by the Teichmüller space, which was the subject of Nag's book. And there are interesting measures, so interesting ways of sampling these Riemann surfaces, which are originally were mathematically motivated, and then there were different measures which were proposed by string theorists. But anyway, so these are all different models of random two-dimensional geometries, which can be studied using these using matrix integrals. And now matrix integrals are, so these are integrals over matrices, and by matrices, and these are kind of highly simplified versions of gauge theories. So gauge theories are what we use to describe interactions between elementary particles. So the light in which you see these slides is carried, as you know, by electromagnetic waves, which is the, so these are the excitations of the simplest gauge field, the abelian gauge field. And we are built out of atoms, and so atoms have electrons and nuclei are held together by other kinds of gauge interactions, strong and then weak forces. And so all of them are examples of four-dimensional gauge theory. And so it would be interesting to see what if we replace the zero-dimensional gauge theory, which gives some kind of two-dimensional random geometries, by high-dimensional ones. So going up in dimension now means two things. So we can either increase the dimension of the space on which these matrices live, or we can try to directly increase the dimension of the geometry which we try to randomize, so to explore. So the combinatorics of matrix integrals correspond to two-dimensional geometries. And if you try to replace 2 dimensions by 3 dimensions, then there is an obvious generalization which replaces trivalent vertices by 4-valent kind of 3-dimensional objects. The building blocks, the blocks built around the tetrahedron as opposed to triangles. So that would be described by the generalization of a matrix model called the tensor model, where the matrices which have 2 indices, now replaced by tensors which have 3 indices. And so you can attach these 4 tensors using the tetrahedron, and that gives you some kind of interaction of that. So there was some interest in these models in recent years, where people realized that, well, you can really find correspondence between the Feynman rules, so the rules of computing approximately the integrals over these tensors, to three-dimensional manifolds. Unfortunately, there are 2 unfortunate things. So first of all, this tensor theory is much more complicated than gauge theory. So going from 2 indices to 3 indices really changes things a lot. There is no analog of the genus. On the other hand, for 3 manifolds, the topology of 3 manifolds is much more sophisticated than the topology of 2 manifolds. So in 2-dimensional manifolds, if they are orientable, they are only characterized by the number of handles, the so-called genus, which you can compute combinatorially using Euler's formula. There's a number of vertices minus number of edges plus a number of triangles. In 3 dimensions, this combinatorics always gives you 0. The Euler characteristics of any compact 3-manifold is 0. There is no obvious analog of genus. There is no obvious way of organizing the sum over 3-dimensional topologies into something in some kind of complexity. So in the context of the Sajdev-Fourier-Kitaev model, which I mentioned, so the specific models of one-dimensional particles interacting with some disorder or spins. So SY and K propose different models which are equivalent in some limit. There is a way of simplifying the perturbative expansion, but it's not clear what is the topological feature which the simplification captures. So in this talk, instead, so I will not follow this route, I'll just offer this as a kind of review of what people tried. I will discuss models of random geometries in 1, 2, and 3 dimensions, which are motivated, which I did not study them because I wanted to study random geometries. I came across these models because I was interested in the study of strong interactions. So I was studying quantum gauge theories in dimensions 2 and higher, and relative close cousin topological string theories in dimension 6. And somehow it turns out that the analysis of these completely different subjects brought a host of statistical mechanical models or combinatorial models which happen to model random geometries. So I do not claim that these models quantize Einstein gravity. So there isn't some emergent geometry, but it is not governed by Einstein equations. But it turns out that among the plethora of examples which we will discuss, 2 of these models, which deal with 3-dimensional geometries, happen to contain, if you look at them with the trained eye, the emergent 11-dimensional geometry of 11-dimensional supergravity or M theory, and even something beyond that. And so that's interesting for people at least in the community of string theory and supergravity. So let me tell you something about the way these models are organized. So they will be built on partitions. So partitions we will discuss, but one way to understand the random geometry in dimension D, so D in my case will be 1, 2, and 3, or 4, is from some model which describes growing structures. So if you have a structure in 1 dimension higher, then the boundary of this growing structure will be the kind of fluctuating geometry in dimension d. So if you think about three-dimensional crystal, like take a cube of salt, right? And then if the environment is moist, then the sharp edges of this cube of salt will eventually melt. And so the boundary, which is two-dimensional, will have a shape which will change in time with some fluctuations, but on average it will approximate something smooth, which is the example of emergent geometry. So this idea can be carried in some number of dimensions, not in arbitrary, and that's the models which we will explore. So now people say that mathematics started with counting. So of course, what were people counting? They were counting in Egypt mostly taxes. So it was so mathematics. Part of the mathematics came from actually accounting. So you owe me 1, 2, 3 bushels of wheat, and so these are just amounts of number of objects without structure. I was told that the first mathematician whose name was Thought in Egypt, he actually extended this idea of accounting all the way to infinity. So he invented natural numbers and actual infinity, which is maybe the pharaoh wanted to have an infinite amount of tax collected from his subjects, or I don't know what, but that's the myth. But eventually, also tax collectors, they were picky, so they were thinking that if these 3 bushels of wheat are different from those 3 bushels of wheat because maybe one of them is rotten or something, and so you start getting interested in the structure of objects which you're counting, and so this is it's one way of coming to a notion of a partition. So number 1 is just number 1. There's no way to split it into smaller non-zero numbers, but number 2 can come in two kind of forms. It could be 2, or it could be 1 plus 1. And 3 can be 3, or 2 plus 1, or 1 plus 1 plus 1. So these are objects with structure. So if you think that this 3 came by joining 3 ones, this joining could be done in different ways. And so this is what the usual partitions, or these pictures are called Young diagrams. So this is what they represent. So if I have 2 such squares, I can attach them to each other in 2 ways, and so that will give me 2 partitions of 2. If I have 3 of them, I can have 3 ways, which will give me 3 partitions of 3. But if I have 4, then the number will be not 4, but will be something else. And okay, I will mention that guy later. So another way where you can encounter these partitions is, I don't know if you do gardening or actually construction. You're familiar with construction. Everything is construction here. So when you do construction, you need to carry bricks, right? So you can take a cart and try to fill it with bricks. So you drop them, and if you just drop them, and they follow the law of gravity, then they can form some structures which will look like the Young diagram, but maybe slightly rotated. And if you just drop them at random, so start dropping bricks at random, then the structure which you will get will be different, even though you may start with the same number of bricks, but the final shape these bricks will assume, you will have choices. So, for example, so if I start adding bricks by one, by the time let's say I got to 5 bricks, well, I could arrive at this configuration of 5 bricks in different ways. I could have, right, so maybe, so this, so I could arrive here by following this route, so by adding one, and then one from this side, and then from this side, and then one from this side, or I can start adding one from this side, and then at the last moment add one from this side. So there are two ways of arriving at this picture, and many more ways, like 5 ways to arrive at this picture, and this continues. So it's the possibilities of growth, they are enumerated by the paths on the infinite graph, which is called Young graph, because every vertex is a Young diagram. And so you can set up a model of random partitions where, so your random variables will be Young diagrams or partitions, and the probability of a given partition lambda will be proportional to the number of ways it can be built out of nothing times the number of ways it can be reduced to nothing. So it's some kind of a path which number of paths on the Young graph, which start at the start here, goes some distance, passes through the partition you're interested in, and then comes back. So this is counting number of paths to reach from empty my partition and back. I call this quantum bricks because this is the way we compute probabilities in quantum mechanics. So this measure happens to be quite famous. So I call this probability distribution a measure. This is a language borrowed from probability theory. Even though this is a kind of discrete, so it's a measure on a finite set. If you fix the size of the partition, it turns out that, well, you can compute the actual value of the probability of a given partition, and it turns out to be proportional to the inverse product of the squares of the hook lengths of all boxes in the diagram. So for this square, the hook length is the number of boxes to the right, which is 4, plus the number of boxes below, which is 2 plus 1. So it's the hook of this guy is 7. And so you take a product over all little squares, this hook length of this box, you take a square, and then there are some normalization factors. So this quantity happens to have a meaning in the representation theory of the permutation group, a group of permutations of absolute value of as many elements as the number of squares.
What is the capital lambda?
It's a parameter of this measure. So in statistical physics, we have 2 types of ensembles. One is called microcanonical ensemble, and another is called grand canonical ensemble. So there are 2 ways of setting up the problem here. One is to say that I will fix the number of squares, and so I will have a finite number of partitions with that number of squares, and that number was explored by Srinivasan and Ramanujan, the asymptotics of that number. And just study this probability distribution on this finite but large set of partitions with a given size. Or I could say that the size is unbounded, but then there is some quantity which is called the chemical potential or fugacity, which couples to the size of the partition. And so this capital lambda is this fugacity for that way of setting up the problem. And the claim is that with this exponential factor, this becomes really a probability measure. Namely, if I sum over all partitions of all sizes from 0 to infinity, this sum is equal to 1. And the way to see that is to use the fact which I quote but I don't explain, is that this quantity, which is a product of hook lengths, inverse product of hook lengths, is equal to the square of the dimension of the representation of symmetric group, which happens to be labeled by this Young diagram. And so then in representation theory of finite groups, there's a theorem due to Heaviside which says that if you take all irreducible representations of the group, take the square of the dimensions and sum over all representations, you will get the number of elements in this group. And so this lambda factorial is the number of elements in the group of permutations. And so then when you sum over all lambdas, this will become just the series for the exponential, power series for exponential. Okay, so this, by the way, so this story was of interest to mathematicians in 1970s, so like early 1970s. This was one of these interesting examples of the same idea coming to people living on the opposite sides of the globe. So there was a group of mathematicians in St. Petersburg, at the time Leningrad, Vershik and Kerov, who were interested in the properties of representations of groups when you send some parameters to infinity. Like, for example, take a symmetric group and ask what is the most probable representation of the symmetric group if you send the size of the group to infinity. And that's a question of maximizing this quantity given, let's say, the size of the diagram, and maybe rescale the diagram so that it will keep, the picture will have a finite size, but make the number of boxes go into infinity. So it means that the size of individual box will go to 0. And so the boundary will become kind of a continuous curve, which is called the limit shape. So which we will get to later. So that was the Vershik-Kerov problem in Soviet Union, and in the US, it was simultaneously, really miraculously, because the miracle is that there was no communication, of course, so that's why it's a miracle. It was studied by Logan and Shep. I mean, I don't know what else Logan and Shep were working on, but Vershik and Kerov, of course, they explored this asymptotic representation theory quite a lot. And one of the outcomes of this theory is the huge development in the theory of symmetric functions, which nowadays we have a great book by Ian MacDonald about the and so this is just one of the examples of measures which one can get from symmetric functions. But, so this is from the 70s, so can you imagine the surprise of some of us which found that such measures and major generalizations arise from doing something completely different, namely integrating, computing integrals of something, some real measures now, because these are now continuous, integrals of continuous spaces. So averaging over this modular space of solutions of some partial differential equations. So you have some partial differential equations defined in terms of field variables which live in 4 dimensions. And so so you have equations which are motivated by physics. These equations have many solutions. They form the whole spaces, modular spaces. Physics also gives some measures of the spaces, so some ways of averaging over the solutions. And remarkably, these integrals happen to be equal to finite sums. So, so as if these modular spaces could be chopped up into pieces, such that for each piece you can compute the integral exactly, and it will be given by the value of the measure from, like, for example, p lambda or some generalization of it. And then, so these discrete objects we were summing over these partitions actually label ways of chopping up the continuous modular space into meaningful pieces. And moreover, so this Plancherel measure and these generalizations, they actually happen to be the simplest examples of the exact WKB approximation. So usually, if you're familiar with the approximate calculations of integrals, especially if your integral has some kind of exponential or oscillating factor in the integrand, then there are approximate methods of computing the integrals by looking at the saddle point, the critical point of the exponential, and that gives you kind of way of estimating the integral. But these integrals, which I came to study, turned out to be given, not approximately given by the contributions of those saddle points, but exactly. And so this exact evaluation happened to be equal to the computations of averages in the models of random partitions. So here we encounter some notation which is non-technical. So it's a modular space. So it's a space of parameters of solutions to some partial differential equations, which in this case happen to be the equations, so-called instant-on equations or or antecedent duality equations. And here I just quoted a picture from Wikipedia, which describes some of the solutions to these equations in kind of artistic form. So these are the profiles of, so there is some field, there is some energy which you can associate to this field. This energy is distributed in space-time. And these are just examples of solutions. And we want to integrate over all solutions. We integrate, I mean, of course, the trick is what is it that you're integrating. So this is something which I will not be able to explain in the non-technical lecture. But it is something which is well motivated, let me put it this way. So the interesting thing is that the problem of quantum field theory from which these integrals came from offers also generalizations of the original problem which mathematicians came to from their perspective. So one thing which the four-dimensional origin of these integrals gives is that in 4 dimensions, when we analyze the solutions of the partial differential equations, we do that using the symmetries of the 4-dimensional space-time, and in particular the rotations. And so in 4 dimensions, 4 Euclidean dimensions, the generic rotation, so isometry which preserves a point, has 2 parameters. So the general rotations in 4 dimensions is just 2 rotations on 2 orthogonal planes. And so there is a 2-parametric family of problems which are parameterized by these 2 angles of rotations, and these give the generalizations or refinements of this Planck-Schrödinger measure, which you can find in MacDonald's book related to the so-called Jack polynomials. So for interesting gauge theories, the ones which describe strong interactions, so strong interactions bind quarks inside the nucleons, and quarks have the so-called colors. So we believe they have 3 colors, but we can study the generalizations of gauge theory where the number of colors is an arbitrary number. And so it turns out that if you look at the equations of gauge theory for the n-color gauge theory, the saddle points which give the exact value of the integral of the modular space are now in correspondence with n-tuples of partitions. So not one Young diagram, but n Young diagrams. And so these happen to be the best way to visualize them and also interpret the measure, the probability, is to generalize this gardening card picture to the geometry which now has n angles. So there's 1 angle, 2, 3. So this is for n equals 3. And so then you start dropping the bricks which get stuck at the corners. And so this is the example of a configuration with 3 Young diagrams. I had to squeeze the shape to fit them into this geometry, but So there is a systematic way of doing this. And so that way, the study of collections of Young diagrams becomes the model of piecewise linear one-dimensional geometries. So this is the boundary of the picture. So this green line, it's a curve, which is locally is just straight line, but the more features you add, the more the slope of this curve can change. And so in the limit, it becomes kind of a almost everywhere differentiable curve called limit shape. And so that curve is the simplest example of geometry which you should compare it to the solution of Einstein equations. So there is some effective action which this geometry extremizes, the analog of Einstein-Hilbert action, which I should stress comes from studying quantum gauge theory. So it was a gauge theory in 4 space-time dimensions, out of which emerged kind of effective one-dimensional geometry, which is not in our 4-dimensional space-time. So it's a geometry living in a different space.
Sorry. So this is the correspondence is in a saddle point. Is it? So is it like
It's a saddle point in the space of all saddle points, actually. So
okay. So in that limit, there is this correspondence, but there could be fluctuations about this saddle point, which is not captured by this formula, or is it?
So you can, so the saddle point dominates the integral in the limit when these parameters corresponding to rotations ascend to 0. But if they are not 0 but just very small, then there are fluctuations around this shape, which one can systematically study. Right.
But then the formula that you wrote about the integrals and equality.
The formula is true for any value of these parameters.
Yes.
But what this formula tells you is that the gauge theory computation becomes equal to statistical mechanics of random piecewise linear geometries. And then there is a parameter, or there are several parameters in the statistical mechanics, such that it will be dominated by something almost smooth, which looks like normal geometry, but there are fluctuations. So this is what we want. We want to have weakly quantum geometry, so weakly fluctuating geometry. So this is the picture for an SU3 gauge theory. So there are 3 corners here. If you want SU4, it will be 4 corners. If you have so this is whether this is pure gauge theory or theory with quarks enters the kernel which describes the energy of this configuration. But it could be pure glue theory or could be theory with matter fields.
Okay. Thank you.
Okay, so it turns out that the analogous partition functions can be defined not only for 4-dimensional theories, but also for 4, 5, 6, 7, 8, 9-dimensional theories, and using embedding to string theory for greater if we are beyond 4 dimensions. And these computations can be used to test some predictions of string theory, which are by now also very old, already like 30 years old. And those predictions, among other things, contain the prediction that in string theory, which is normally believed to live in 10 space-time dimensions, once you resum certain non-perturbative effects, you will find yourself living in 1 dimension higher. So there is an emergent dimension coming out. And it turns out that some of these things can be tested without building extremely expensive accelerators, which will never reach the energies needed for string theory. but just doing some combinatorics, which you can do to some extent using McDonald, but at some point you have to go beyond McDonald. So a slight generalization of the measure which I talked about before now uses the refined version of the hook. Unfortunately, the picture which I had to steal from the internet uses not the traditional, I think, French way of drawing Young diagrams, which is what I used here, but it uses, maybe it's Anglo-Saxon way. It uses the rotated version where things are rotated by 180 degrees, which is probably French or Japanese. And so this is actually, so this is called A of the box, the arm length. So it's a number of boxes to the right. And this is called L of the box, the leg length. So imagine that for normal Young diagram, if my heart is at the box and I put the arm, so it's a number of boxes to the right, and if I'm standing on one leg, it's the number of boxes I'm standing on. So it's a refinement of this hook formula. The hook is the arm, arm plus leg plus 1. And so this is the refinement of that previous formula, which depends on additional parameters, which is motivated by doing gauge theory in 4 + 1 dimensions. What is quite unexpected is that this complicated sum over all partitions can be reorganized into something which is called the platistic exponent. So you know what normal exponent is, but the platistic exponent is something which you find, again, in McDonald's book on symmetric functions, where you have a function of the same arguments as your original function, and then you raise each argument to the power k, when k goes from 1 to infinity, divide by k and sum. And so this is, well, in physics, this has to do with the way to organize the partition functions of systems of indistinguishable particles. So if you have a system of k particles which travel in periodic time and come back, so they can do this in different ways. They can either travel by preserving the individuality, or they can get permuted because they're indistinguishable. And so when you think about the ways, the combinatorics of the space of trajectories on the spaces of indistinguishable particles, you will come to the realization that you can organize the sum over all possible permutations the configurations of particles can undergo into the cycles. So the symmetric, every permutation is a product of cycles. And so this exponent is just a sum of the elementary cycles of length k. And denominator k is just the fact that if you have a cycle which contains k elements, it has a symmetry of order k. So it's just some motivation. So the beauty of this example is that it says that the original formula, which was the sum of the partitions, this is the result of doing some kind of analysis, quantum mechanical analysis, on the same modular space of solutions to some PDE defined in 4 dimensions. But this platistic exponent turns out to be a new interesting mathematical function called the elliptic genus, and that can be attributed to fields which live in 6 dimensions. So quantum mechanics on the modular space of solutions of some operations in 4 dimensions, that's studying like 1-parametric families of 4-dimensional fields, so it's a 5-dimensional problem. But here you have something which lives on the product of 2-dimensional torus and R4, and that's 6-dimensional. So there is an emergent dimension, whole dimension, which emerged out of the accounting of these partitions. And of course, this function, this platistic exponent, you actually know from well, from many things. And one is that if you, this function is a generalization of quite a famous function. So if you set all these refined parameters mu q to 1, just only keep the fugacity for the number of partitions, then this whole thing collapses to the generating function of the number of partitions, which has this famous product form, which was first computed by Leonhard Euler and was studied by Harding Ramanujan. And so Ramanujan famously was given small corrections to the asymptotics of this number P of n for large n by Kali in his dreams. So there is an asymptotic formula which you can, the first term of which you can derive by doing the saddle point in the Fourier integral, but then there are saddle 1 over the 24th, which is very hard to explain, but which sometimes make this asymptotic formula actually exact. So it's one of these interesting mysteries of how the mind works. Anyway, one can go to high dimensions, and instead of two-dimensional partitions, which were Young diagrams, which you could draw on a piece of paper, on a two-dimensional paper, which are built out of squares, you can now study the combinatorics of cubes. So if you ever had to move, so you pack your stuff into boxes, and then sometimes you need to put your boxes in the corner of the room so that they occupy the least space possible, but then there are different ways of stacking them up, right? And so that's the way of organizing three-dimensional partitions or plane partitions. But now the way to visualize them, so this is a projection to a two-dimensional plane done by my co-author and colleague Andrei Okunkov, and we will return to this picture later. So this counts of three-dimensional partitions arise in the problems which are formulated in 6 dimensions. So there is some modular space of solutions of PDE, of some PDEs in 6 dimensions, integrating over which you come with the sums over plane partitions. So plane partitions have now, so these are stacks of cubes, but they can also be viewed as the collections of ordinary partitions organized inside one Young diagram. So this partition function, again, is a generalization of something quite famous, namely if you set this refining parameters having to do with rotations of 6-dimensional space to 1, you will get just a generating function of the numbers of plane partitions, so just which was computed first by Percy McMahon. And so it looks like a very simple generalization of Euler's formula. So instead of the product 1 minus p to the n, you have this extra factor of n. So Percy McMahon was, as you know, I think he was a colonel in the British Army stationed here in Madras at the time. Then he got sick, he got honorable discharge, went to England, and became a mathematician, interested in among other things, in combinatorics. And but he didn't know that a certain refinement of this study of the enumeration of partitions, which, as I said, you can only understand it if you realize plane partitions as special points on the modular space of solutions of some PDEs in 6 dimensions, actually contains, by this resummation, not 1, but actually 4 extra dimensions. And so this partition function secretly knows about the supergravity in 11, so 10 space and 1 time dimension. So these parameters, the parameters of rotations and fugacity for the number of cubes reorganizes itself into a symmetric function of 5 constraint variables, which happens to be the supergravity partition function. So now Percy McMahon wrote a book, a textbook, where he conjectured, or maybe he claimed actually it was correct, a formula for the number of partitions in any number of dimensions. And so we'll come to that. But, so following McMahon, we would like to ask, should we stop at 3 dimensions, or maybe we can go to 4 dimensions and try to enumerate arrangements of hypercubes. So we start with squares in 2 dimensions, then we went to cubes in 3 dimensions. Let's go to hypercubes in 4 dimensions.
So the 2-dimensional boxes was for the permutation.
Right.
And the cubes that have still the permutation, or is that?
No, so the cubes, so for cubes, the analogy is the following, that 2-dimensional boxes, you could representation of symmetric groups, but also there is a so-called Hall duality. They also label representations of the unitary group. So that gets generalized to the Kac-Moody groups when you go to higher dimensions. And so the plane partitions, it's not really quite finished branch of representation theory, but people now associate plane partitions to representations of the so-called toroidal algebras. So these are highly infinite dimensional algebras, but very, very interesting. So they generalize ordinary groups to loop groups to double loop groups, and they are the algebras. Right. So the question which arises is how to visualize 4-dimensional partitions, because we live in 3 dimensions, and so hypercubes are something which is complicated. So we use the projection we can use the projection of R4 to R3 along the axis 1, 1, 1, just like we did without explaining that for plane partitions, I took the arrangement of cubes and projected it to the 2-dimensional plane along the 1, 1, 1 axis. So if you take your ordinary cube and project it along the main diagonal, what you see 3 rhombi, right? So these beautiful pictures, which are generated by Okounkov, so they have 3 colors. These 3 colors represent 3 rhombi of different orientations. And so the plane partition, or the arrangement of cubes, is just the combinatorics of attaching rhombi to each other. So by analogy, if we take a hypercube, we will get a kind of tessellation of R3 by cuboids, so kind of squished cubes with some interesting angles. And so just by analogy, so we had this, the projection of a 3-dimensional partition whose boundary was really a 2-dimensional fluctuating geometry, was a tessellation of R2 by rhombi. Now the tessellation of R3 by cuboids is a random 3-dimensional geometry, which comes from something simple defined, something defined on sorted partitions, which are the arrangements of hypercubes.
So those were some perfect matching, right?
Well, I'm not sure. So perfect matching is a technical term. So they're perfect in the sense that there's no empty space between them, and so the edges match exactly, right? So
Is there an analog for these?
yes, so in that sense, it's as perfect as they are, except that, so for rhombi you had three basic orientations. For cuboids you will have 4. Now this happens. So just the count of solid partitions happens to be a famous problem, which was undertook by Percy McMahon. And so this generalizes the previous, so the formula for the ordinary partitions is due to Euler, it has this product form. Then the plane partitions formula was conjectured, I think, by McMahon, and it's actually, this is the correct formula, it has been proven. One of the proofs you can find in the book by MacDonald, but there are other proofs. And so you can see, so you have the exponent here is 1, then it becomes n. So McMahon thought that maybe these are binomial coefficients. And so he conjectured this formula, and you can actually test it, and so it gives the right answer for the partitions of size 1, 2, 3, 4, 5. So every physicist, every sane physicist would tell you that if you have a formula which works correctly in the first 5 cases, it should be correct. But for 6, the formula of McMahon gives an error of 1. So just instead of 140, which is the correct number, it gives 141. So it's an error of less than 1%. But it turns out to be the end of this formula. So it's not the right formula. And to this day, so it's more than 100 years later, nobody knows whether just the account of solid partitions can be actually expressed by a formula. So people try to write some kind of product formula. So if you have a power series, you can always formally represent it as a product of alternate maybe factors 1 minus 2 to the n to some exponent, but these exponents turn out to be quite chaotic. So my former student, Navin Prabhakar, when he was an undergraduate student, he assisted in some of these computations. And so people, of course, know the asymptotics for large n, what this number of partitions should look like because of just some geometric considerations, but they don't know the exact formula. And my colleague and collaborator, Andrei Okhenkov, always told me that, well, whatever you do, so you can study partitions in 2 dimensions, you can study partitions in 3 dimensions, they have interesting emergent geometry and fluctuating properties, but whatever you do, don't study 4-dimensional partitions. That's a bad problem, and there are some arguments from Landau, actually, of why you don't expect to have a nice limit shape in this problem. But it turns out that the gauge theory, which has these 4-dimensional Young diagrams as special points on the modular space of solutions to its equations, gives you different measure. So it tells you that you don't have to, it's not the right thing to just count them directly without any structure. They have some structure. And so the normal approach is to count the solid partitions in a kind of refined way, which generalizes these refined ways we had for the ordinary and plane partitions, but it just turns out that for 4 dimensions, there's no simplification. So there's no simpler, simpler specification of parameters for which this supersymmetric measure will become just constant, unlike the previous cases. So it turns out that there is a refinement, again, so you have to keep the parameters which correspond to some rotational symmetry. So this time the PDEs which one studies are formulated in 8 dimensions. So there are 4 rotation parameters, but the rotations, the symmetry of the equations is not of all possible rotations, but of rotations of special kind. So they belong to a subgroup of SU4. And so there are only 3 independent parameters. And so the partition sums, which one can set up for multiple solid partitions. And remarkably, so one can compute so this is done, of course, this was done originally by kind of brute force, by lots of experiments. And the results of these experiments show that the partition function has the pletistic exponent, the form of pletistic exponent. And of course, when I first observed that there is this chance that the formula will simplify, I remembered the fate of Percy McMahon, so I had to test this for 1, 2, 3, 4, 5, 6. And of course, when it worked for 6, I said, okay, maybe it's true, but 6 is actually not too large. So the really interesting case is when you can form a hypercube, arrangement of hypercubes, which is itself a hypercube of size 2, 2 by 2 by 2 by 2. So it means you have to go to 16. And at the level of 16, the number of those partitions is of the order of 100,000. So you want to check a formula which contains, it was actually 120,000. So 120,000 terms. So it's 120,000 terms. Each term is some rational function of this many parameters. So, well, it seems like hopeless exercise because there are signs one can guess for these formulas if you try to just fit. And if you have 120,000 terms and each term comes with a sign which you don't have a systematic way of writing, then the number of choices you have to make to come up with to verify it even with supercomputer, it will be the time will be longer than the age of the universe. So,
What about machine learning?
yeah. So, but of course, mathematicians are smart. So they tell you the first thing they tell you. So I went to Kontsevich and asked him, how do you check complicated formulas? He said that you never check them with letters. So you don't use them as unknowns. You put random numbers. Then it's very fast to compute. So okay, I said, okay, so that gives me some hope that maybe I'm on the right track. But I really want to check that the formula works. So I had to come up with some scheme. I took my laptop, my postdoc laptop, my own laptop, my daughter's laptop. I connected them all. I split this problem into many sub-problems, and I fed the results into the new laptops and so on. And so it took me 2 weeks. And of course, these were kind of a nerve-wracking 2 weeks because you make one mistake and then this whole exercise is over. You have to start over. And then I remember that in the 50s, when people were, in fact, in the 40s, when people were working on Manhattan Project, or in the Soviet equivalent of that, people had to calculate the rates of nuclear reactions, and they had no computers. And so how did they do that? Well, they had the whole rooms full of calculators. Who were the calculators? Well, they were careful girls who were just carefully doing simple computations and then feeding the results of their computations to the next girls. And so they were supervisors, and so they were human computers. And people did this incredible computation. So, 70 years later, I'm sitting in my office and doing computation. Instead of many calculators, I just have 5 laptops. So but it's the same kind of situation. Anyway, so nowadays, there are some mathematicians who claim that they are now prove this formula. To be honest, I cannot check the proofs. But I think it's a remarkable formula. And it contains all the previous formulas which I showed you before as special cases, and some generalizations, but it doesn't allow you to, so far nobody came up with the choice of the parameters for this formula which will give you the original McMahon problem. So it turns out that the supersymmetric count of sorted partitions, it counts them with signs so that on average, these 4-dimensional structures, they actually look like 3-dimensional structures. But then there's no specific 3 dimensions aside 4 dimensions which they prefer. So kind of fractal structures inside the four-dimensional space, which are more or less three-dimensional. Now, the puzzle which is of interest for physicists is that the count of plane partitions, I told you, contains the 11-dimensional supergravity. And that's the maximal, kind of the maximal theory we know of. We don't know anything beyond 11 dimensions, nothing supersymmetric. And this, somehow, the success of these computations relies on some kind of supersymmetry. So what is the physics of these partition functions of solid partitions? We don't know, but it's very suggestive. So there is something beyond 11 dimensions. Maybe it's a non-Poincare supersymmetry. And what is the emergent geometry? We don't know. So I hope I partially entertain you by flying over a range of dimensions and models of gauge theories motivated by interactions of elementary particles, which, so the motivation is by natural phenomena, but then there is some leap of imagination motivated by mathematics of these theories, which leads to models from which geometries of spaces different from the geometry of original gauge theory emerge. So where do we fit in this picture? I leave you to ponder upon. Thank you.
Thank you for such a beautiful talk. Questions?
So you said this partitioning can give you high dimensional connections, right?
Yes.
So is there any property of this partition which tells that this higher dimension is compact or non-compact?
So the phenomenology of these things is the following, that whenever you have a platistic exponent expression for the partition function, the free energy, which is this quantity here, has a denominator. And in all previous cases, this denominator, the number of factors in this denominator was the number of complex space dimensions. So, for example, here, so there was 5 factors in the denominator, and that corresponded to 10 dimensions of space in 11-dimensional supergravity. So this guy has 6 factors in the denominator, so naively it suggests 12-dimensional space or 13-dimensional space-time. But it could be that so these factors have different roles. So maybe these are complex and this is real, but it's not clear. But at least the denominator is the number of bosonic degrees of freedom. So whether they are holomorphic or real, that might be a subject of debate, of interpretation. Yes.
Are there any generalizations of this partition calculations for non-supersymmetric gauge theory?
So, right. So for non-supersymmetric field theories, what disappears, so several things, so there are kind of things are becoming worse in several layers. So for one thing, the exactness of WKB approximation disappears. So there is for any saddle point in the path integral, there is an infinite perturbation series. The second thing is that the number of saddle points grows considerably. So there, in addition to instantons, which were discussed here, there are many saddle points which are not instantons at all. So we know very little about them. And the third thing is that most likely most of the saddle points are truly complex. So they require moving into the space of complex fields. And so we know very little about them. So most likely the simple combinatorics will be vastly generalized.
If there are like instanton ions kind of thing which are magnetically charged, are there any simplifications?
Well, without supersymmetry, there's no argument, there's no reason even to say that even the instantons are the correct saddle points. So most likely there are instantons and instanton endians and many other things which are not even known. Yes.
Sorry, I missed the overall picture. So here you said that if you start with the known gauge theories and then you go to the smooth limit, you get something other than Einstein
Right.
gravity. But
Right.
I guess what we are interested is in the other direction.
Right. So the
And so
question
these-
is, so here I was playing with gauge theories I could analyze. So maybe the lesson here is that we should generalize gauge theories so that on the side of when there's some emergent geometry, we will get something which looks more like the Einstein.
What does that mean, generalized gauge theory? In what sense? What do you?
More matter fields, more sophisticated gauge groups. So here I presented for you very simple examples where the gauge group was just SUN. Tomorrow I will talk about theories where the gauge group has many factors, like in the standard model. That already gives something more interesting, and also different types of gauge groups. So the analysis which I presented is done for unitary gauge groups. Nobody knows how to generalize it already to orthogonal symplectic ones, but there are other groups also which we study in high energy physics. So that is still an open question.
So I guess nobody knows, which particular construction will give us Einstein. And you were talking about Euclidean structure, I suppose.
This is done in Euclid. So even though when I mentioned space-time, but in all truthfulness, the space-times I was talking about here were Euclidean space-times. So it's the mystery of actual time is still mystery.
Is it known how to take these ideas and then go to Minkowski space-time?
Not really.
No.
Not
Okay.
really. So here time was, I mentioned, I mentioned several times that I was working in 4+1, 6+1, 8+1 dimensions. So +1 was time, but this time was kind of a periodic time of a circle where one computes a trace. So when you compute some kind of trace in field theory, time doesn't, there is nothing interesting happening in time.
You mentioned about permutation cycles at some point.
Yes.
I know that in the case of interacting bosons, like liquid helium-4, Feynman's theory brings in permutation cycles in an explicit way and converts into a classical problem. I wonder if there is any...
Well, here this effective bosons and fermions, which one sees in the partition function, they are non-interacting. So one can turn on interaction, but it will not because of supersymmetry, the permutation symmetry will not be broken. So it's so this phenomena of strongly interacting bosons don't occur.
Okay, so we call it a day. Let's thank the speaker again, Professor Microsoft. Thanks for participating.